I would like to talk about rational functions and their graphs. Rational functions look like fractions, except in the top and the bottom, we have expressions instead of numbers. So an example of the most basic rational function is going to be a new parent graph of f of x equals 1 over x. It's the reciprocal function. And if we have a coordinate plane, this graph has this dotted line thing where the two axes are. And the graph is in two sections, one up here and the other down here. Now, this graph is called a hyperbola. It has two legs. And we can see as this graph moves out this way, it gets closer and closer and closer to the x-axis, but it's never going to touch it. In other words, as x approaches positive infinity, y, or f of x, approaches what? As x gets closer and closer and closer to infinity, we get closer and closer and closer to the x-axis. F of x would approach 0. Over here, as x approaches negative infinity, as we move farther and farther to the left, f of x also approaches 0. It gets closer and closer to 0 without touching it. That's an A on the end there, hyperbola. So this is different than the end behavior of a polynomial function. Polynomial function, it either approached infinity or it approached negative infinity. It either rose forever or fell forever. With these rational functions, with the graphs of the hyperbolas, we're approaching this dotted line. It's not always going to be the x-axis. For instance, if we moved this graph up, the dotted thing that we get closer and closer to would also move up. This notation, as x approaches negative infinity, as x approaches positive infinity, we've done that notation before. But I want to introduce another notation as x approaches 0 with this little minus sign up here. The minus sign indicates from the negative direction, from the negatives. So this actually means as x approaches 0 from the left. I could do better than that. Negative from the negative direction means from the left. There we go. So as x approaches 0 from the left, what happens? As x approaches 0 from the left, we're going to get closer and closer to this line, but we're never going to hit it. But where are we going? as x approaches 0 from the left, we're getting closer and closer to x equals 0. We're never hitting it, but our y value is getting closer and closer to negative infinity. As we approach 0 from the left, we fall. We approach negative infinity. What about as x approaches 0 from the right? What do you think that notation is going to be? From the left, from the negative side was a little minus as an exponent. As x approaches 0 with a plus there means as x approaches 0 from the right. So as x approaches 0 from the right, we're swinging up. So from the right, f of x would approach positive infinity. So we approach x equals 0, this dotted line from the right. What happens to the graph? It's swinging up. Closer and closer we get to 0, the closer the output is going to get to positive infinity. So that's what asymptotes do. We approach, and get closer and closer and closer, and we never hit it. In fact, it's going to bend us up towards positive infinity, down towards negative infinity. And then as we're going outwards, it's going to bend and we're going to approach 0 or whatever the horizontal dotted line will be. Now, I've been calling it a horizontal dotted line because I didn't want to introduce the true name yet. These dotted lines are called asymptotes. And we have 3 different kinds of asymptotes. We have vertical asymptotes. That's the vertical dotted line. We have horizontal asymptotes. That's the horizontal dotted line. And we're also going to have a slant, also called an oblique asymptote. That's a diagonal. And we have those instead of horizontal sometime. So we'll have vertical asymptotes and we'll have horizontal or slant asymptotes. And today we're going to identify them from graphs. We're going to identify them from their equations, and we're going to learn how we can graph these things. Okay, sorry about that. So let's look at this graph. Let's say we have one, two, three, 4, 5, 6. This will be a vertical asymptote. And what would the equation of this vertical asymptote be? Well, if this was just a line, which is really all it is, 1, 2, 3, 4, 5, 6, and it hits the x-axis, this is x equals 6. And we're going to have a horizontal asymptote. Here. And what's the equation of this horizontal asymptote? Well, if it were a line, and it is just a line, it would be a horizontal line that strikes the y-axis at 4. Horizontal asymptote is y equals 4. Another way of saying that in function notation would be f of x equals 4. So vertical asymptote at x equals 6, a horizontal asymptote of y or f of x equals 4. Let me go ahead and put in the legs of this graph, actually draw the hyperbola itself. The asymptotes are not part of the graph. They're just telling us where the hyperbola bends. Okay, so there's our hyperbola. There's the legs. Let's fill in these questions. As x approaches negative infinity, f of x approaches what? And then we'll fill in as x approaches positive infinity, f of x approaches what? As x approaches negative infinity, that means as x gets farther and farther to the left. Well, f of x is getting closer and closer to this horizontal asymptote. F of x is approaching 4, but it'll never hit 4. Asymptotes tell us where the function does not exist. Whatever this function is, if we were to put a whole bunch of different x values in, it'd get closer and closer to an output of 4, 3.9, 3.99, 3.999, 3.9999999, 3.999999999999999, but we're never going to hit 4. Over here, as x approaches positive infinity, as x goes farther and farther to the right, f of x also approaches 4. So the horizontal asymptote tells us basically the end behavior of the rational function. Here's a graph, a new one, of the function 1 over x squared. This hyperbola is a little weird because instead of being in opposite corners, we still have our same horizontal and vertical asymptotes as 1 over x. But these are in side-by-side sections. So as x approaches infinity and as x approaches negative infinity, f of x approaches 0. But as x approaches 0 from either the left or the right, f of x approaches positive infinity. As x approaches 0 from the left, f of x approaches infinity. As x approaches 0 from the left, it curves up. As x approaches 0 from the right, from the positive side, f of x also approaches infinity. Okay, just wanted to mention that. We might come back to that later. We might not. It might be one of the graphs we move around. We'll see. I want to start focusing just on vertical asymptotes for now and how we can identify them from a given function. Now, just to draw something out here, vertical asymptotes tell us, well, they strike the x-axis, so they're x equals lines. They would tell us things that x cannot be. In other words, the vertical asymptotes tell us what we can't have in the domain. And remember, domain of something like f of x equals 2 over x minus 3. What can't we have? Well, we can't have 0 on the bottom. So we take the bottom, we say it can't equal 0. If we solve, that means here x can't be 3. And if x can't be 3, 1, 2, 3, that means we'll put a vertical asymptote at x equals 3. What if we had more than one thing? What if we were looking at a new function g of x, and this was x minus 4 over 3x squared plus 5x minus 2. Well, we can't tell what our restricted values are because it's not in factored form. So step 1 is always going to be factor top and bottom. Rather than clutter this, I'm going to move off to the side to do my factoring. This is a 3x squared, so the airplane method tells me put in a 3x and a 3x. Since that's actually 9x squared, we know we're going to need a corrective step at the end. Something's going to divide away. A times c, 3 times negative 2. We need numbers that multiply to negative 6, add to positive 5. These numbers would be positive 6 and negative 1. So I'm going to put in plus 6 minus 1. The corrective step would happen here, dividing both by 3. That gives us x plus 2 times 3x minus 1, or whatever your preferred way of factoring is, but you will need to be able to factor that. And now we can see that x plus 2 can't be 0, but also 3x minus 1 can't be 0. Those would cause us to get 0 in the denominator. They would cause us to be undefined overall. So x can't be negative 2. Add 1. 3x can't be 1, so x can't be positive 1/3. So here we would have 2 vertical asymptotes, positive 1/3 and negative 2. On the graph, at negative 2, there would be a dotted vertical line. On the graph, at positive 1/3, there would be a dotted vertical line. 2 vertical asymptotes. What? Now, I'm not going to draw this exact one, but yeah, we can have 2 vertical asymptotes. This graph might look like this. Something hyperbolic will happen on the outsides, and then something kind of parabolic will happen in the middle. Finding points and plugging them in is going to be what helps us find these actual graphs. You may or may not get that far today. I think we might. I think we might. Let's find the vertical asymptotes here of k of x equals 4x squared over x squared plus 4. Well, if we try to factor the bottom, we can't. X squared plus 4, sum of squares, we can't factor that. In fact, we see if we take the bottom and set it equal or not equal to 0, let's set it equal. It'll be easier to show you what's happening if I say equals. What are the values of x that make this true? Well, x squared equals -4. We can't take the square root of a negative number in the real numbers. And when we're graphing, asymptotes have to be real numbers for us to be able to find them and put them on the graph. So this has no solution, which means there are no values that cause the bottom to be 0, which means this one has no vertical asymptotes. None. Okay, let's do one more. We're going to find the vertical asymptotes of x plus 4. I guess we'll give this a function name too. Let's call it h of x. There we go. H of x equals x plus 4 over 2x squared plus 20x plus 42. So let's factor the bottom. We have to find the places where the bottom equals 0 to find the values we can't have for x. If we factor the bottom, and I'll do this over here, 2x squared plus 20x plus 42. We need to factor the 2 out first. We see we have a common factor, bringing us to x squared plus 10x plus 21. If you don't factor the 2 out first, you won't get the correct factorization. We need numbers that multiply to 21, positive 21. We need them to add to positive 10. This is plus 3 and plus 7. So rewriting this in factored form, we have x plus 4 over 2 times x plus 3 times x plus 7. Now, take the bottom, set it equal to 0, find these restricted values. This means 2 can't be 0, x plus 3 can't be 0, and x plus 7 can't be 0. 2 can't be 0. No duh. 2 can't be 0. It's always true. We don't get any values from that. It's not like it says 2x equals 0 and we have to solve. Over here, x plus 3 can't be 0. So if we subtract 3 from both sides, x can't be negative 3. If we subtract 7 from both sides here, we see x can't be negative 7. So even after saying I would make it equals 0, I ended up making it not equals anyway. It really doesn't matter. What you need to do is understand why you're setting this equal to 0. So whether you say equals 0, whether you say not equals 0, just remember you're doing this to find out what you can't have for x. These values would become vertical asymptotes. There will be an exception to that, but happens very rarely, and we'll look at an example later. But as of right now, these vertical asymptotes are going to happen at x equals 3 and x equals negative 3 and x equals negative 7. Again, that's not a solution to this equation. These are vertical asymptotes, negative 3 and negative 7. Now, let's move on to horizontal asymptotes. We're actually going to have 3 cases. One of 3 things is going to happen. If we have a rational function, f of x, and it has some numerator on the top, some denominator on the bottom. On top, we want to find the degree of n. On the bottom, we want to find the degree of d. We want to find the degree of the numerator. We want to find the degree of the denominator. So if the highest power is a squared, then the degree is 2. If the highest power is a fifth, then the degree is 5. The 3 cases then would be that the degree of the numerator is less than the degree of the denominator, or the degree of the numerator is greater than the degree of the denominator. And guess what? Maybe they're both the same. The degree of the numerator equals the degree of the denominator. Degree of the numerator less than the degree of the denominator. An example would be, hey, 1 over x. The degree of the top is 0. The degree of the bottom is 1. Degree of the numerator is less than degree of the denominator. And remember, we started out by looking at the graph of this function. The graph of this function had a horizontal asymptote at 0. horizontal asymptote is going to be y equals 0, just like 1 over x. That's it. There's no other work for that. If the degree of the top is less than the degree of the bottom, the horizontal asymptote is automatically y equals 0, like 1 over x. And the graph of 1 over x can help you remember that. If the degree of the numerator is greater than the degree of the denominator, then the horizontal asymptote is going to be none. There's going to be a slant instead. And we'll talk about how we're going to find that slant, that oblique asymptote, when we get to an example where this happens. Or at the very least, when we get to one that asks for the slant asymptote, as opposed to is there not a horizontal asymptote. If the degrees are the same, this one's my favorite. The horizontal asymptote is going to be y equals a ratio. And it's going to be the ratio of the leading coefficients. And again, when we get to an example of this, I'm going to show you what y equals ratio of the leading coefficients is. This one is the easiest, if you don't consider that the easiest. This really isn't so bad. This looks complicated, but when we're working through the 3 cases, more and more examples, you're going to see, okay, it's not hard. I just have to remember the cases. So let's look at f of x equals 8x squared plus 1 over x to the 4th plus 1. The degree of the top is 2. Highest power we have is a squared, so the degree is 2. The degree of the bottom is 4. Highest power we have is a 4th, so the degree is 4. When the degree of the top is less, that's just like 1 over x. Just like 1 over x, the horizontal asymptote would be y equals 0. That's all the thought that has to go into that. The degree is smaller on top, just like 1 over x. So just like 1 over x, it has a horizontal asymptote of y equals 0. Now let's say we have g of x equals 2x cubed minus 6x all over x squared plus 4. The degree of the top is 3. The degree of the bottom is 2. The degree is bigger on the top than on the bottom. So the answer to what's the horizontal asymptotes would be none. We would instead have a slant asymptote. And we're not going to find that here. None is an acceptable answer. All because the degree of the top was bigger. That means no horizontal asymptote. Let's look at h of x. This is going to be 8x squared plus 9x minus 5 all over 2x squared plus 1. This one, like I said, is my favorite. The degree of the top is 2. The degree of the bottom is 2. Highest power of both is an x squared. So to find the horizontal asymptote, here's exactly what we're going to do. It's going to be y equals a ratio of the leading coefficients. Those x squareds, what are the coefficients? 8 over 2. Horizontal asymptote of y equals 4. When the degrees are the same, the ratio of the leading coefficients gives us our horizontal asymptote. 8 over 2 is 4. You say, what? I say, yep. Now, I want to look at this further. And I'm going to use some magic to clean this up a little bit, but I want to look at h of x again. There we go, magic, see? All that circling, all that mess is gone. We found that the horizontal asymptote was y equals 4, or f of x equals 4. Two x squared plus 1 on the bottom. This is going to be one of those ones that doesn't have a vertical asymptote. Remember that the horizontal asymptote, that's telling us what we approach for a function value, for a y value. In this case, we're approaching 4 as x approaches positive or negative infinity. So as we get farther out, we're getting closer and closer and never crossing it. But that doesn't mean anything on the inside. So this particular one kind of looks like this. We have no idea how to do this yet. And being able to graph this isn't actually going to be important. But as you can see, as we approach as we approach negative infinity, as x goes farther and farther to the left, we're going to get closer and closer to 4, but we're never going to cross it. Here, as we approach positive infinity, we're going to get closer and closer to 4, but we're never going to cross it. But in the middle, we actually do cross it somewhere. So a follow-up question that you might be asked is, okay, you found the horizontal asymptote. Where, if anywhere, does it cross the horizontal asymptote? And what we're going to do is set the function equal to our horizontal asymptote and then solve for x. So where do we cross the horizontal asymptote of 4 here? We would set the whole thing equal to 4 and solve. So let me move this up so that I have more room to work. 8x squared plus 9x minus 5 over 2x squared plus 1. Again, it's set equal to 4 because that was our horizontal asymptote. We want to start by clearing the fractions. We want to make this a straight line equation. We would multiply both sides by the 2x squared plus 1. That'll cancel that out here, and we'll be left with 4 times 2x squared plus 1 on the left. On the right, we'll just have the 8x squared plus 9x minus 5. And here we go. Time to start solving. Clear parentheses by distribution. 8x squared plus 4 equals 8x squared plus 9x minus 5. If we subtract the 8x from both sides, we're just left with 4 equals 9x minus 5. Add 5 to both sides, 9x equals 9. Divide both sides by 9, we get x equals 1. So where are we going to cross the horizontal asymptote? It's going to happen when x equals 1. Specifically, the point 1 what? 1, 4. And again, if I drew what this graph kind of looks like, isn't it fun when I have to draw? Okay. See, it'll cross it at y equals 4, and we just solved to find that that x value would be 1. So the 0.14. Okay. Graphing right now, not important. Being able to find that point, though, that is important. Find the horizontal asymptote, and if it asks you, hey, what point does it cross that? Set it equal to the number, solve to get the x value. The eraser got in a puddle of water. And now it's all a mess. Okay, I'm gonna let that dry for a second. Okay. Let's take a look at f of x equals 4x squared plus 8x minus 5 over x squared plus 7. We're going to find the horizontal asymptotes as part A. And for part B, where do we cross the horizontal asymptote? So, degree of the top is 2, degree of the bottom is 2. Squared is the highest power we have for both. So the horizontal asymptote will be a ratio of the leading coefficients. That ratio is 4 over 1. So y equals 4 is the horizontal asymptote. Where do we cross the horizontal asymptote? Well, we'll take our function that we were given, And since the horizontal asymptote was 4, we will set it equal to 4 and solve. Multiplying both sides by the x squared plus 7 gets rid of the fraction on the right. Cancels. We have 4 times the x squared plus 7 on the left. Distribute 4x squared plus 28 equals 4x squared plus 8x minus 5. Subtract 4x squared from both sides, leaves us with 28 equals 8x minus 5. Add 5 to both sides, 33 equals 8x. Divide both sides by 8, and we get that we cross the horizontal asymptote at divide by 8, divide by 8, 33 eighths. So the point would be 33 eighths 4. Horizontal asymptote of 4. We cross at 33 eighths 4. Same questions. Horizontal asymptote, and where do we cross? New function. S of x equals 5x plus 25 over x squared plus 9x minus 5. Degree of the top is 1. Degree of the bottom is 2. The degree of the numerator is less than the degree of the denominator. That is just like 1 over x. So automatically y equals 0 is the horizontal asymptote. Where do we cross? Well, let's set the whole thing to 0. Why are we setting it equal to 0? Because that was our horizontal asymptote. Multiplying both sides by the denominator to get rid of the fraction. 0 times anything is 0. So that's just like having the top equal to 0. So negative 25 equals 5x. Divide both sides by 5. We get x equals negative 5. The point then would be negative 5, 0, where we cross. So we have a horizontal asymptote at y equals 0, but we are going to cross it at negative 5, 0. Okay. If we have f of x equals x squared minus 6x minus 6 all over x minus 7. We see that the degree of the top is greater than the degree of the bottom. That means horizontal asymptote, there is none. The degree of the top is greater than the degree of the bottom. There's no horizontal asymptote because we have a slant asymptote. Let's find it. All we do is synthetic division. That does come back here. And if we do synthetic division, we're dividing by x minus what? X minus 7. 7 goes in the box. We have coefficients of 1, -6, and -6. Let's do the work. Bring down the 1. Multiply and add. Multiply and add. What we would get, it's an x squared that we're bringing down. We would have x plus 1, and then a remainder of plus 1 over x minus 7. This would be the actual division. The slant asymptote, we throw away the remainder. And y equals x plus 1 would be the slant asymptote. That's all we do to find a slant asymptote. What would be the vertical asymptote? Vertical asymptote, x minus 7 couldn't be 0, so x can't be positive 7. Vertical asymptote of x equals 7. So if we graphed these asymptotes, x equals 1, 2, 3, 4, 5, 6, 7, and then y equals x plus 1. That is a y-intercept of 1 and a slope of positive 1. See, a slant asymptote is literally a slant asymptote. Here it's the graph of the line y equals x plus 1. And then let's test some value. Let's plug, for instance, x equals 1 in. If we plug x equals 1 in, that would be 1 squared minus 6 times 1 minus 6 over 1 minus 7. That would be 1 minus 6 minus 6 over negative 6. Negative 11 over negative 6 would be positive 11/6. So at 1, positive 11/6, just a little bit under 2, that'd be a point right here. This tells me that we're in here for that leg, because this point just under that slant asymptote is on the graph. So that must mean we're filling in this area following the rules of asymptotes. And if we're in here, I'm going to guess if we come over and plug 8 in, we're going to end up in this area. Let's test that out. Let's make sure. If I plug 8 in, I would get 8 squared minus 6 times 8 minus 6 all over 8 minus 7. That's 64 minus 48 minus 6 all over 1. 64 minus 48 is 16, minus 6 is 10. So over here at x equals 8, I'm going to be up here at 10. So yeah, I'm up in that area. So instead of it being a straightforward blah, blah, the horizontal one slants, but we're still in there. And the more accurate we are, the more points we pick for x, the closer we can see where these hyperbola legs actually are. Okay. Let us, I'm trying to find another good just slant asymptote problem. Let's take a look at f of x equals 2x squared minus 5x minus 3. This is all over x minus 2. Horizontal asymptote, none. Degree of the top is greater than degree of the bottom. So we do synthetic division. X minus what? X minus 2. 2 goes in the box. 2, negative 5, negative 3. Bring down the first number, multiply and add. Multiply and add. Throw the remainder away. Y equals 2x minus 1 then would be the slant asymptote. What's the vertical asymptote? Well, I'd like to just say off the bat that the vertical asymptote is 2. But we can't really just say that. Remember, earlier I said there's going to be an exception. It's going to be rare, and we'll talk about it when we get there. This one isn't going to be an exception, but I'm going to show you how to check and make sure. I've been all about factoring the bottom and then setting those equal to 0 and being able to find vertical asymptotes. But sometimes if we factor everything, something cancels away from the bottom. It would still not be in the domain. It would still be a restricted value, but it won't be an asymptote. The only way we can know for sure is to make sure we factor the top as well. So here, if we factored this, I'll do it off to the side. I need numbers that multiply to negative 6, 2 times negative 3, add to negative 5. These numbers are negative 6 and positive 1. If I put that in the airplane method, I would need a 2x and a 2x because of my 2x squared. But I'll also need a corrective step because 2x times 2x is actually 4x squared. Put in my minus 6, put in my plus 1. Both of these divide by 2. So we get x minus 3 times 2x plus 1. Notice nothing cancels. So we're good to say that x minus 2 equals 0 will give us a vertical asymptote. Add 2 to both sides, that vertical asymptote would be x equals 2. we had found the slant asymptote of 2x minus 1. So on the graph, x equals 2. Oops. This is something like that, y equals 2x minus 1. And here, we're actually going to be bending on these ones. How do we know? Well, if I picked something to the right, what would this be? There was a vertical asymptote of 2. If I plugged 3 into the original function, and I'll actually use factored form here, 2x plus 1 times x minus 3 all over x minus 2. If I plug 3 in, I get 7 times 0 all over 1. That would be 0. So when I plug 3 in, I get a y of 0. That means I have a point right here. And that tells me I'm in this section. And if I'm in this section, odds are I'm in the one diagonally across from it. We can check that by, seeing where we are when x equals 0. Are we above the slant asymptote or are we below? If we're below, we'd fill in down here. Since we're above, that means we're in this section. It has to be that leg. Let's look at our exception. One where it might actually be a thing. Let's look at f of x equals x squared plus x minus 30 all over x minus 5. Here's why I don't want you to jump and say vertical asymptote x equals 5. Because if we factored this, we would get x minus 5 on the bottom still. On top, the two numbers that multiply to negative 30 and add to positive 1 would be positive 6 and negative 5. And look what happens. This function actually simplifies to just x plus 6, but we have a restricted value where x can't be 5. It's not an asymptote, though. Because it doesn't bend the graph. This is simply going to be the linear function y equals x plus 6 with a hole at x equals 5, not a vertical asymptote. One, two, three, four, five, 6 is up here. And at x equals 1, 2, 3, 4, 5, this was a bad place to draw it because I need to be right in here. Okay, let me move it over here. One, two, three, four, five, 6 on the x-intercept, a slope of 1. So that's this line here. but at 2, 3, 4, 5, up here, an asymptote would bend us. This is just going to be a little hole, a point in the graph that doesn't exist. So the domain would still have to exclude 5. The domain would be negative infinity to positive 5, and then we get rid of the positive 5 and we continue to infinity. That would be the domain, but the vertical asymptote would be none. Because since that x minus 5 cancels away, it just leaves us a hole in a simpler graph, not an asymptote that'll bend us into a hyperbola. How can we find the value of that hole? Well, we simplified this to y equals x plus 6. We know x can't be 5. If x were 5 and we plugged it in, the y value would be 5 plus 6. It would be 11. So the hole is at the point 5, 11. So you'd plug it in to find the y value of the hole.